All right. So let us begin this today's session. And this is the last session for the course Operation and Planning of Power Distribution Systems. And in this session, we have already covered 12 tutorial session for 12 assignments separately. Now in this session, this is the extra session. In this session, we will briefly revise all the tutorials, means all the concepts means that are important for uh, you can say your exam. Means like we will see all the whatever the theory part we have learned and in a brief and in short, and then we will see also the problems that we have already solved for this course. So let us start from the course contents. And if you see the course contents, like this has been divided into 14 parts. First one is introduction, power delivery system, a brief overview, and then we have seen history and development of electric power system, Indian power system and overview. And the module 1 tells about load characteristics and load management, and module 2 about power distribution network. And then we have reliability assessment of distribution network, and then we have seen various power quality issues. After that, we have seen load flow analysis of radial distribution network. In that, we have seen backward forward load sweep method, and then we have reactive power compensation of distribution system with shunt capacitors. We have seen the sizing and placement of shunt capacitor for radial feeders. And then we have coming to this economic aspects of power distribution planning. And then we have different models and solution strategy for distribution system planning, where we have seen about the optimization problem and what are the strategy for solving that. And then we have seen reconfiguration of power distribution network, and this is also most focused towards this optimization part. And then we have seen distribution system with this DG, distributed generation, and then we have energy storage system and distribution system automation as smart grid. So what we do, we will just see the theory of each big, and then we will see the assignments that we have already submitted, so that we can revise what are the problems, typical problems that can be asked in the exam. So beginning with the big one, where we have seen introduction, overview, and load modeling. So we know that what is the where we have interconnected power systems and how they are. Now we have one nation, one grid, one frequency, and its advantage are reliability, better economy. And if you see the history of electric power, we know that this Holmes Edison introduced DC system, and Westinghouse Tesla introduced AC system, and they have the power bar, means bar between these two DC and AC system, is quite famous. And certainly this AC power system gained popularity due to the invention of transformer. Now our how the power industry restructures. So you can see this restructuring of power systems. These are theoretical part. And what is the definition of power systems? Power system means all aspects of generation, transmission, distribution, and supply of electricity, and that includes one or more of the flowing, and it puts all parts like from generating station to transmission system and to the load side to the distribution system that have overhead line, service line, electrical supply line, distribution line. And this is the brief discussion about how this history means how our national grid reforms, means how this comes into one nation, one grid, one frequency, and that came in December 2013. And if you see before 1991, we have 5 regional grids, and how it has evolved to one nation, one grid, one frequency. Then you can see our power delivery systems, that how we have divided the power systems into sub parts. First, we have generating station, and its rating is 1020 kV, and power rating is typically of 500 megawatt. If you have 4 generating stations, then it will be 4 cross 500 megawatt. And then we have transmission systems, And in transmission system, we have tie lines to connect the other parts, other systems, other transmission systems. Then we have sub transmission systems. Its rating is 120 kV, 110 kV, 66 kV. When the form substantial system, large industrial consumers may be connected, and they also connected to small local independent power producers. And after subtransmission system, we have distribution substations from where our this course is focused. And if you see this, first comes primary distribution systems, and that is a rating of 33 kV, 11 kV, where medium large consumers are connected, or maybe some DG are connected, like wind generation system. And then from primary distribution systems, we have secondary distribution systems where they are connected to a small consumers like our households. And we have seen single line diagram that is used for tracing power transmission distribution networks. And top one is shown for balance. It is single line diagram we draw for the balance system. So it is for shown for a typical example shown for the single line diagram, and below structure is for transmission system, and we know the transmission system is usually of mesh type. So that's why they have many power flow paths. Mesh system means we have many power flow paths, while radium system have unique power flow path. So coming to the difference between transmission network and distribution network. So if you see, the first major difference is a transmission network is of mesh type, while distribution network is of radial type. And in transmission side, load is of relatively balanced, while distribution network load is of unbalanced type due to single phase loads. Transmission network is of transposed type, while distribution network is of non-transposed type. Power losses is low in transmission network, while in distribution network power losses is quite high. Fault tolerance is less in transmission network, while fault occurrence is more in distribution network. RxY-S ratio is low in transmission network, and this is high in distribution network. So that's why this power losses also low in transmission network and high in distribution network. So let us see what do you mean by load. So an electrical load is a device which consumes certain amount of power and energy to accomplish certain tasks. So you should not define load by its resistance or impedance. You should define the load by the power consumption. So based on the dependency of voltage, our loads are are of three different types. First one is constant power load. So here power is constant regardless of voltage. Example, electrical motors, constant current load where power is proportional to voltage. And examples are welding units, smelting and electroplating processes, etc. And then we have constant impedance load where power is proportional to voltage required, and examples are incandescent lighting, resistive water heaters. Now, what do you mean by load curve and load duration curve? So electrical load varies with time, we know that, and this plot of load demand with respect to time, that is called known as load curve. While load duration curve is recorded from a load curve based on the descending order of load magnitude. And area under load curve is equal to area under the load duration curve, that is amount of energy consumption. And next we have important expression about regarding load factor. So load factor is the ratio of average demand to the peak demand. And the important thing about load factor is that load factor near to unity is preferable to utilities. It means average demand and peak demand should be close to each other. And load factor is lowest for domestic type of load and highest for industrial type of load. So if you have this average demand equal to peak demand, so it is hypothetical load curve and it does not exist. Then coming to this load characteristics and load management module, where we have seen several expression. The first one is load factor, that is ratio of average demand upon peak demand. And among domestic, commercial, industrial, agricultural loads, we have these domestic loads have lowest load factor that comes between 10 to 15%, while industrial loads have highest load factor and its percentage is 60 to 65%. Higher load factor near to unity is preferred to utilities. It means average demand and peak demand should be close to each other. So daily load factor is the ratio of daily energy consumed on peak demand into 24. So here, if daily or annual load factor comes, then the ratio comes in the form of energy, while simply load factor is defined in the terms of power, and 1 unit of energy equal to 1 kilowatt of hour. Now we have seen load curve and load duration curve. We know that our electrical load varies with time, and the the plot of load demand with time is load curve, while load duration curve is the recorded from load curve based on the descending order of load magnitude. And area under load curve equal to area under load duration curve, that is equal to amount of energy consumption. In the dual system, number of nodes equal to number of lines plus one. So here you can see there are 3 nodes and we have 2 lines. And we have already seen what is the difference between transmission and distribution network. And this we have also seen. So today we have 1 people present. So what we will do Gudu means like we will just see all the theoretical parts, all the basic concepts, and then we will see the current year assignment also, so that will be helpful in your current exam.
Okay,
So
sir.
next we have diversity factor, that is the ratio of some individual peak demand upon a group peak demand. So in diversity factor, you should know about what we mean by this coincidence demand or non-coincidence demand. So non-coincidence demand means that is sum of individual peak demand, while coincidence demand, it is the group peak demand. And coincidence factor is the reciprocal of diversity factor. So therefore diversity factor is greater than 1, while coincidence factor is less than 1. Demand factor, the maximum demand upon total connected load. So demand factor is always less than equal to 1. And what do you mean load diversity? Load diversity is sum of individual peak demand. It is a subtraction of difference of sum of individual peak demand and group peak demand. So it may ask you the class contribution factor. So class contribution factor you can also find from this method, where we have defined this coincidence peak demand in terms of individual peak demand and the contribution factor. So the relation between coincidence peak demand or group peak demand and this contribution factor and individual peak demand is given by this expression, where this CI is the contribution factor and P group max is group peak demand, aggregate peak demand, or coincidence peak demand. Now, how you will find the calculation of contribution factor from the table you have provided. So you can first find out the time instant at which the group peak demand is occurring, and then you can find the class contribution factor by seeing that first you find the time instant, and from the and at that time instant you see that class demand at time of system peak upon class non-constant maximum demand. So you have to see that class only. So loss factor, now loss factor is the average power loss upon power loss at peak load demand. So loss factor is similar to load factor, where we have load factor the average demand of peak demand, while loss factor there this loss will come average power loss upon peak power loss. And then we have utilization factor. Utilization factor is the maximum demand system upon rated system capacity, and utilization factor is same as the demand factor. We know that demand factor is maximum demand upon total connected load. So till here we can see the first week assignment. And if you have any doubt, then you can ask. Otherwise, I will just continue. So I have bind up all the tutorials, all the tutorial solutions. So if you see first problem, which of the following is the correct which of the following is the correct hierarchy of the power system. So if you just from the top, first generation system comes, then transmission system, sub transmission system, primary distribution system, secondary distribution system. So it is quite easy one. And then in the second problem, which of the following is are of feature of transmission system? So it is multiple thread type. So we know that transmission system is of mesh type and it is of transpose type, while radial and high power loss are characteristics of distribution system. Third problem, which of the following substation equipment gives the capacity rating of substation? So which of the following? First, the transformer only provides the capacity rating of substation. So transformer is the correct answer. Circuit breaker is not correct. Metering equipment, these are all wrong. Transformer only provides the rating of substation. Which of the following is constant power load? So it is just like power alternation. In power alternation, switches provided the rating of your converter. So here in for substation, the transformer provides the rating of substation. In power tonic converter, the switches provides the rating of converter. Now, which of the following is constant power load? So we have seen the constant power loads. So this electrical motor comes under constant power load. What is active distribution networks? So distribution network with DG distribution generation, we call it as active distribution network, where bidirectional power flow is possible. What is the assumption to draw the single line diagram of a power network? So the assumption we have taken to draw the single line diagram is balanced. The network should be of balanced type. Then distribution feeder consumes 240 units of energy in a day. Daily load factor of the feeder is 0.50. Determine the peak load on the feeder. So we have energy consumption given. So based on the energy consumption, we can get the average demand. So average demand we found from the divided by the number of hours, and then peak demand we have to find, and it is also given the load factor. So load factor is known as the average demand upon the peak demand. So we will get the peak demand is equal of 20 megawatt, 20 kilowatt. Now with number problem, the lightning load which is operating from 6 p.m. to 6 a.m. daily at constant demand of 200 kilowatt, and from 6 a.m. to 1 p.m. at constant demand of 100 kilowatt. The load demand of the rest of time of the day zero, the load factor for this load is. So you need to find the average demand. We know that load factor is average demand upon peak demand. The load factor is average demand of peak demand. So if you need to find the average demand, how will you find? So it is given that lightning load having constant demand of 200 kilowatt. Anyway, so 200 kilowatt is from 12 hours, while 6 a.m. to 1 p.m. we have constant demand of 100 kilowatt. So it is 6 a.m. to 1 p.m. 7 hours, and the load demand for the rest of time is 0. So 200 into 12 plus 100 into 7 upon 24, that is average demand, and maximum demand is of 200 kilowatt. So its load factor comes out as 0.646. Now it is asking about the load curve and load duration curve. We know that load curve and load duration curve both have the same area. Which of the following is a measure of to understand the change in load demand. So we don't define the load by its resistance or impedance. We define the load by its power consumption. So B is the correct answer. Good to till here. If you have any doubt,
No, sir.
okay, then we will see the next part, that is demand side management. So demand side management is nothing but it is the approach towards improving the efficiency and cost effectiveness of energy usage on the customer side of the meter. And this is achieved by shaping the load characteristics, either daily load characteristic, weekly load characteristic, or monthly or annual load characteristic. And this does not include outage or interruption. So whatever demand side management you are doing, so this you have to keep in mind. Sorry, you have to keep in mind that it does not include the outage and interruptions. The power supply remains intact. So first one is energy saving or conservation programs, and second one is second category load management programs. So in first uh, category, we generally encourage our consumers to use the less, to use the more, to use the energy efficient equipment, and how to save the electricity. And in load management programs, we have it is done by utilities to reduce the demand periods to make the more economic use of existing resources for demand displacement over time. So the means of demand side management, first one is peak saving or peak clipping. So from the name, you can see that we are clipping the peak power. So this peak power demand reduces. So you can say that peak demand reduces and total energy consumption also reduces. Valley filling means like we have peak demand. So during off peak hours, we are we are we are encouraging the consumers to use the power, to use the energy, let's say electrical energy. So this off peak hours, it will power consumption will increase. So you can see that peak demand remains same while total energy consumption increases. And next we have load shifting. So in load shifting, we are shifting shifting the power consumption from the peak hours to off peak hours. So it will reduce the peak demand and total energy consumption will remain same. And by shifting, your load factor will increase, and that is desirable for the utility. A strategic consumption means like you are shifting the whole load curve downwards. So in this we have peak demand and total energy consumption both reduces. While load growth means both peak demand and energy consumption increases. Now let us come to this energy rate structure or tariff structure. So how the tariff structures, what are the different ways of tariff structures? So they are of many types. These are of a flat demand data structure, block meter data structure, demand data structure, season data structure, or time of day structure. In flat demand data structure, we have constant a constant price per kilowatt hour, where a fixed amount of INR is charged for a per unit of energy. While block meter structure, we have lower prices for greater usage. So there are different charges for different slots of energy consumption. So for first duration, first 50 kilowatt hour, let us say it is of 10 INR, and then after 50 kilowatt hour, this prices will get reduced to 8 INR or 5 INR, 5 rupees. Then we have demand data structure. We have separate charges for demand energy. That means we have separate charges for power energy. So that is demand data structure. And next we have season data structure. We have higher prices per kilowatt hour used during the season, and we have when the system peak demands occur. So during it may be applied in summer season, we have higher prices per kilowatt hour because the peak demand increases due to the more usage of our air conditioner. And time of day, it is just like season data structure. We have higher prices during peak demand for a certain season, and here we have higher prices for a peak period of the day, and lower prices during off peak period of the day. So let us see the second number assignment based on the whatever we have just discussed. We have just briefly revised. So if you go through this slides also, you will easily know that you will easily find that you will easily solve the problems. There will be no uh, chances of mistakes. If you have gone through these slides, you can easily solve the assignment problems. So coming to the assignment number 2. So in this first problem, we have different a radial distribution feeder having 10 nodes, and among that 5 nodes are of residential loads, and 3 nodes are of industrial loads, and 2 nodes are of commercial load nodes. The maximum demand for residential, industrial, and commercial load are of 40 kilowatt, 120, and 100 kilowatt. Total energy consumption is 600 units on the same day, with 15% of energy loss occurring daily due to the ohmic loss. So in this first problem, they are asking that if the residential load consume 20% of the total feeder consumption, find the load factor for the residential load. So we will first find the average demand. Average demand we will find from the energy consumptions, and peak demand is already given. So average demand is 20% of total energy consumption, so 120 units, while maximum demand is given as 40 kilowatt. So load factor will come as accordingly. Now next problem, we have total connected commercial load is of 900 kilowatt. Find the demand factor for the commercial load. So demand factor, we know that peak demand upon total connected loads. Demand factor is maximum demand upon total connected load. So we know that demand factor is maximum demand upon total connected load. So maximum demand is of 100 kilowatt for the commercial load, while total connected load is of 900 kilowatt. So we'll get the demand factor accordingly. In the next problem, we have diversity factor. So diversity factor is sum of individual peak demand upon the group peak demand. So sum of individual peak demand you can find from the data given, and the feeder peak demand they have provided, that is group peak demand. So this one is group peak demand. So feeder peak demand is group peak demand. Do you know what is the difference between group peak demand and individual peak demand?
Group peak demand. No idea, sir.
So you revise it carefully, otherwise it will be difficult to solve in the exam. So like in this problem, if you see, we are solving this first problem of assignment 2. So here, this for residential, industrial and commercial loads, we have individual peak demand of 40 kilowatt, 120 kilowatt and 100 kilowatt. While
Mm.
this is not a group peak demand, means like a distribution feeder is providing power to all these type of loads, but we cannot say that group peak demand is any of one of them. Means it is not like that here 120 kilowatt is higher, so it will be of group peak demand. With group peak demand, we have to either in the problem it is given, or you need to find from the table if the table is provided. So see here they provided this peak demand of the feeder is 180 kilowatt. So if you see individual peak demand for residential, industrial and commercial are different, 40 kilowatt, 120 kilowatt, 100 kilowatt, while peak demand for the radial feeder is given as 180 kilowatt. So that is the difference. Did you got this point?
Okay, sir.
So now next we have feeder loss factor. So feeder loss factor is similar to this load factor. Here this loss factor comes. So average power loss and peak power loss you can find from the data. So you just see this problem. Next we have area under the load curve presents. So area under load curve certainly will give you the energy consumption. So it will, yes. Next we have power station has a maximum demand of 1500 kilowatt and the annual load factor is 50% and plant capacity factor is 40%. What is the reserve capacity of plant? So we have seen plant capacity factor. So plant capacity factor is annual energy produced upon the maximum plant rating. So from there you can find the maximum plant rating, and once you find the maximum plant rating and from the load factor you will get the maximum demand. So now the reserve capacity is plant capacity minus maximum demand. So that will provide you the reserve capacity. So from the capacity factor you find the plant rating, and from the load factor you find the maximum demand. Therefore this reserve capacity is nothing but whatever the plant rating and the maximum demand, that is the difference of the both. Means reserve capacity, what do you mean? Reserve capacity is like we have this much plant rating, but the maximum demand is not able to utilize all our capacity. So whatever the remaining amount of power, that is the reserve capacity. So that it is. So you will get the reserve capacity. Next we have which of flowing is are correct. So we have seen that demand factor is peak demand upon total connected load. So demand factor is always less than 1, while load factor is average load upon peak demand, so it is always less than 1. So this is correct, while diversity factor is greater than 1 because it is sum of individual peak demand upon the maximum demand of power station. And coincidence factor is less than 1 because it is reciprocal of diversity factor. Now for question 8 to 10, we have we have a curve, load curve is given, and we can find the load factor. So load factor is the average load upon peak demand. So average load, you take the area upon time, and peak demand is of peak demand is of 80 megawatt. That is happening at a starting time. And plant capacity factor is the actual average load upon plant capacity, means maximum plant rating. So we will get the plant capacity factor. And Claisen factor is the peak demand upon plant capacity. So this is till here for the assignment 2. So now coming to this our module 2, power distribution networks, a brief overview. So we know that our primary distribution networks are mostly of radial topology, which results in indirectional power flow, while radial topology is preferred for its simplicity in construction, cost effectiveness, and protection management. So radial topology has advantages also. It's simple construction. It's simple construction, cost effectiveness, and protection management is also easier. Now, what is the circuit breaker and isolator? Circuit breaker operates at on-load condition, and the function of circuit breaker that it trips and isolated the fault area. While isolator operation is that it bursts at no load condition and it performs circuit breaker maintenance. Now let us see the difference between sectionalizing switches and tie line switches. So Guddu, can you tell the difference between sectionalizing switches and tie line switches? Just measure one major difference.
Sectionalizing open LV bus and circuit breaker. Difference between where is the fault. Sectionalizing indicated open switch, and open switch is the sectionalizing switch, sir.
No, open switch is not sectionalized. Sectionalizing switches, it comes under one area. So sectionalizing switch is normally of closed pipe. If you see sectionalized switch, and whenever there is fault on some side, then we open the sectionalizing switch. While tie line switches it used to add take power from the other feeder area. Tie line switches are normally open type. So tie line switches is used to connect it allow us to take power from other area if our primary feeder is unable to provide power to that area. So you can, and this one is very important. You should know about, you should have clear about sectionalizing switches and tie line switches.
Here in the slide, open switch is the closed line. This is the sectionalized switch indicated. Sectionalized switch, sir. Open switch.
Yeah, sectionalized switches is are of no here I am tell you just interpreted wrongly. So this I am telling that whenever fault happens, like suppose fault happens here, so this sectionalized normally it is a closed type, so it becomes open. So it's better remove. Like initially it is closed, but when fault happens, what happens that it opens. That is
When
the
fault then open, sir, switch.
yeah, it opens and it removes the faulty part, and the other part remains. It provided the power. Our primary feeder is providing the power to other parts. when fault happens in some parts, it sectionalized switch removes that part. Sectionalizer means what? Means it is like bifurcating some part of some areas. You can learn by that way. And tie line switches means it is connecting the other parts, other areas. And tie line switches are also present in our transmission system also. And this is distribution. We are studying our distribution system, so you can get idea from there. So tie line switches are available in transmission line also, where tie line switches are have normally of open type, and whenever we want to provide the power from other areas to certain part of area, we connect it, we closed it. So that's why we call it as used in emergency condition or maintenance condition, because your primary feeder is unable to provide the power whenever some maintenance is happening or some emergency condition, means some fault happens in your this circuit breaker, where this when some fault happens at the initial point of primary feeder, then your feeder will not provide the power to the areas to which it is connected. So it have to take the power from other areas. So in that sense, silent switches will close, and it takes power, it provides power from the other part of area, from the other feeders. You got my point or not?
Got so.
Yeah. Now here we can see the uh, what do you mean by primary feeder, lateral and sublaterals. So primary feeder with the main feeder from which the all parts are connected, means all laterals are connected. So here you can see this this is the primary feeder or main feeder, and through which laterals are connected. And then from laterals we have sublaterals. So these are sublaterals, and this symbol shows transformer fuse, and this symbol shows transformer distribution transformers. Now we can see our bus bar arrangement. So there are of many bus bar arrangements, and it is of so it is shown over here. So we just quickly go through them. So simple one is of a single bus bar with one main power transformer, and then we have with bus synchronizer and two power transformers. And one important scheme is that for bus arrangement is a breaker and half a scheme. And this is very popular and used in many substations. And we call this breaker and half a scheme. Why it is called? Because we are using 3 circuit breakers for 2 feeders. That's why we called it as 3 circuit breaker for 2 feeders, means for 1 feeder we are using 1.5 circuit breaker. So that's why we call it as a breaker and a half a scheme. One, because we are using 1.5 circuit breaker for a feeder. Now you can see the difference between outdoor substation and indoor substation. So outdoor substation requires more space, while indoor substation requires less space. It costs outdoor having is cheaper than indoor. And maintenance is more for outdoor because it is more prone to faults. Fault location is easier because everything is easily visible in outdoor, while it is difficult in indoor. Reliability is lesser in outdoor, while it is higher in indoor. Now comes the uh, means how you can restrict the uh, length of line by which conditions. So for low load density areas, we see the voltage drop. Like for rural areas, we see the voltage drop. Why? while for high load density areas, we see the thermal ampacity of line, or you can see the ampacity limit. So we stick the length of line based on these two, based on this condition. Means like a voltage drop, we see the voltage drop when we are looking for length of line in low load density area like rural areas, while for high load density areas in like industrial or commercial loads, we look for thermal limitation of line or capacity limit of line. So one question is based on this problem. In this problem, it is asked that which is the flowing decisive factor for the permissible length of ruler distribution factor, ruler distribution feeder. Uh, so our ruler distribution feeder is of low load density areas. So we look into the voltage drop. So voltage drop is the decisive factor for deciding the length of line. Now the next question is based on tariff structures, where it is asked that which of fluent tariff is called as block meter structures. In block meter structure, lower prices for greater usage. So B option is correct one. Now let us see the big three assignment, and then we will see the big four assignment. So you just read these two problems, and I'm coming in just 1 minute. Okay. All right. So the first problem is that what is the primary goal of distribution system planning? The first option is to reduce transmission losses. No, it is wrong. Answer is to optimize the utilization of resources to fulfill requirements and future load growth. Yes, we are looking the utilization of resources so that we can fulfill our requirements and load growth. Next problem, in a radial distribution system, power flow is generally of indirectional type. What is the purpose of distribution system reconfiguration? So purpose of distribution system reconfiguration is to minimize the power losses and improve the voltage profile. So indeed this problem is from the, not from this assignment, but it is from the, I think, 10 or 11th assignment. So anyway, from the basic understanding, you can Answer it. Which of the following is used to reduce voltage drops in long radial feeders? So either installing shunt capacitor or reducing the line resistance. Both are ways by which you can reduce the voltage drop in long radial feeders. Which of the following is not a decisive factor for the conductor size? Substation capacity is not a decision factor, while conductor rating, power losses, voltage drop are decision factor for the conductor size. What is a key difference between the primary and secondary distribution network? So the voltage level, we know that in primary distribution network we have voltage level of 11 kV, and secondary distribution network either of 11 kV or 33 kV in primary distribution network, while in secondary distribution network we have 400 volt of voltage level. In power distribution, what is the main purpose of reactive power compensation? And it is for to improve the node voltage and reduce losses. The main objective of load forecasting in power system is to predict the future electricity demand for existing and new customer.
So this type of questions come from current year questions, sir.
Yes,
2025.
current year assignment. So why is ring main system considered more reliable than radial system? Because it has multiple feeding path of four loads. The concept of negawatt emphasizes the negawatt means negative watt. That means the value of reducing electricity consumption. So C is correct. So till here we have covered all the problems till the big three. Now let us see theory for big four. So in big four we have understood about K concept and voltage drop and power loss for different type of distribution areas. Good do you what you do now whenever you speak at the time only you turn on your mic, otherwise keep it off. So K constant defined as the percentage voltage drop per kilovolt ampere mile, and it's expression in R cos theta plus X sin theta, and 1/3 of 1000 upon VR VVS. Its unit is voltage drop per unit upon kVA mile. Now this is the plot of K constant versus copper conductor. So you see that when the copper conductor size increases, this K constant reduces, and whenever this voltage line to line voltage increases, K constant also reduces. So cross section of area increases, K constant decreases. As the line voltage increases, K constant decreases. Now power loss and voltage drop for a radial feeder, primary feeder is given by half of ISZL, and total power loss is half of IS square RL. So you can find the effective length. So for the voltage drop, effective length will be 12 upon 3, while for power loss, this load current is assumed to be concentrated at 8L upon 50. So the distribution substation service area can be of different shape, either it is of a square shape or hexagonal shape. So here we have take assumption before we do analysis on a square substation service area or hexagonal service area. So assumptions are substation is located at the center of service area, and the load distribution is uniform over the entire service area of substation. So we have a square shaped substation area. So here you can see there are 4 primary feeders and laterals are connected to these primary feeders, and notations are like that. A4 means area served by one of the 4 feeders, while L4 means length of primary feeder. And for hexagonal substation service area, we have 6 main feeders, and here notation like is of A6, L6. A6 means area served by one of the 6 feeders. Now substation service area with single and double primary feeders. For single primary feeders, this voltage drop is half of KDLQ. So this comes from the, we have already seen, means effective length is L1 upon 2. So if you substitute voltage drop equal to K L effective into S1, then you will get this expression. And for 2 primary feeders, here A2 will be L2 square, S2 will be D L2 square, L effective will L2 upon 2. So this voltage drop is similar to of single primary feeder, and but for it is at distance of 12 upon 3 from the substation node. Now we will define the general case when we have n number of primary feeders. So when we have n number of primary feeders or more than that, we can define the area served by one of the n feeders is ln square tan theta, where theta is 360 degree upon 2n. Here n is the number of primary feeders, and you can see that if you have value of primary feeders less than 3, then it is not defined, because if you take n is equal to 1, then this tan 180 comes out as 0, while if you take n is equal to 2, this tan 90 comes at infinity. So these all formulas are defined for more than n number of primary feeders when n is less greater than or equal to 3. And then we have KVL load served by one of the feeders is Sn equal to D into An, and then percentage voltage drop will be defined as K into effective length into Sn. And effective length for a main feeder at a distance of 2/3 of ln from the feeder point or from the substation node. So this is the table where you can find the percentage voltage drop step by step. First you have to find the theta. For n equal to 4, we have theta 45. For n equal to 6, that is hexagonal service area. For n equal to 8, that is octagonal service area. Then we will find tan theta. Then we can find the percentage voltage drop. And now you can interpret your voltage drop formula based on this length of feeder, K value, or number of feeders load density, Bismarck effect. If length of feeder is doubled, another quantity remains intact, then your area served by the feeder is also is 4 times, while total KVA becomes 4 times and percentage voltage drop will become 8 times. Similarly, you can find other these cases also. So let us see the big 4 assignment. Then we will see the big 5, that is reliability part. So in the first problem, they are asked about the substance size. So substance size is C into Sn, and Sn we can find from the root 3 VLL into Imax. So Imax is coming from the thermal limit. I think the thermal limit is given 230 ampere. So from that maximum load is found, then substance size you can get. And then we have to find the length of each feeder. So length of each feeder becomes from the KVA served by each feeder. So length you can find from this part. So this problem is for hexagonal substation service area. And next we have to find the service area An. So N is ln square tan theta, and theta for hexagonal substrate surface area is 30 degree. And next we have found to percentage voltage drop. Percentage voltage drop is nothing but K into LE into SN. So we substitute all this effective length and KVA served by each feeder. Then you will get this expression and you will get percentage voltage drop as 12.071%. And now if the load density is doubled, then percentage voltage drop is also gets doubled. So since percentage voltage drop is directly proportional to D, so here you can see that this percentage voltage drop is directly proportional to D. So our percentage voltage drop also gets doubled. Now in the next problem, it is asked about the percentage voltage drop when we have this type of a structure, and these are of concentrated load. So in the first part, is question number 6, they are asking about percentage voltage drop at the end of main feeder. So you just find means for this part, first you find the percentage voltage drop for this part. So it is asking about the percentage voltage drop at this point. So after you apply KLE into SN, so you will get the 7.2%. Now in the next problem, they are asking about the percentage voltage of the primary circuit. Means like whole, you have to assume the laterals and the main feeder. Both are identical, laterals are identical. In the next part, you assume this lateral and you will get the 10.3%, 10.2% is the answer. In question number 8, they are asking about the for thermally limited feeder if the thermal loading is same as for both 6 feeder network and 4 feeder network, which of the following statement are correct. So you can easily find TS6 or TS4. So 6 feeder network carries 1.5 times the load of the 4 feeder network. I'm unable to write here. What is the problem? So if you just divide TS6 upon TS4, so it is 6 upon 4. So it is 1.5 times of 4 feeder network. The value of K constant depends upon the fill of the which of the flame factors. So it depends upon the material used for the conductor, the spacing between lines and type of load. So A and B are correct. So Guddu, can you tell why why it does not depend upon the load density K factor? Are you here?
Yes, sir.
Yes. So do you know why this K factor does not depend upon the load density?
K factors are material used for the conductor. and specific between lines and type of.
Yes, it is the characteristics of the line, so it does not depend upon the load density.
Load density, sir.
It does not depend upon the load density, right?
Yes, sir. Yes, sir. No, magnitude. Load density. It is correct, sir.
It is incorrect. Now, it does not depend upon the load density, because if you see the its expression of a factor, then see here it depends upon power factor. That's why it is depending upon the type of load, but did not depend upon the load density, because there is no D term here. It depends upon the characteristics of the line and the power factor. So material used for the conductor, that that defines its resistance and reactance, and this power factor means this comes type of load, and the spacing between the lines, of course, that decides its inductance. So load density is not correct. Now question number 10, which of the following is a condition for parallel operation transformer? So you have a study in the undergrad course. So all the transformers have same turns ratio, and all the transformers have identical.
Transmission. Yes, sir. Identical. Both are correct, sir.
Mm. So now coming to this reliability part. So let us come to big five. I think now you are in good position to, like we have covered 4 weeks. I think it's a little bit just revised before exam, right?
The here for assignment, all theory are compulsory for solving the questions, sir.
Not all theories, means all theory not compulsory. It's like whatever the question being asked in the problems, that is enough. And you just go through the previous year problems also. Here I am just telling all the parts, all the concepts, because all are correlated. You cannot escape one part without touching other. Means you
How to
all are
solve
correlated.
the problem technique is the important, na, sir.
Yes,
Every question.
yes, correct. Solving the problem is
In
technique
the
you should know.
exam, it is same uh, question line are asking who ask in the assignment questions.
Yes,
That
similar type will be asked, right?
data are only changes, or if it's, statement are also changes.
Yes, correct. Hopefully, I am not confirmed, but hopefully that is the general case.
Yes, sir.
So let us come to big five, where we have seen the reliability assessment. So here we have shown difference between outage and interruption. So outage is the non-availability of operation in certain equipment, while interruption is the loss of service. So outage is of 3 types: forced, scheduled, partial outage, while interruption is of 4 types: scheduled interruption, momentary interruption, temporary interruption, sustained interruption. So schedule means due to scheduled outages, momentary means duration is of few seconds, while temporary means duration is of few minutes, while sustained means duration is of few hours. And if you see outage, post outage means equipment taken out of service on emergency basis, while scheduled outage means equipment taken out of service for preventive maintenance, and partial outage means equipment operational with reduced capacity. So now, what are the Challenges for reliability assessments. So challenges are insufficient data on reliability performance, and most of the interruptions of distribution networks are caused by severe weather related interruptions and for inadequate maintenance. And distribution system reliability can be improved by the timely identification and response to failures. So the reliability indices are of three types. These are indices for sustained interruptions, and these include SAFI, SAIDI, CAFI, CAIDI, ASAI, ASIDI, CTIDI, and indices for momentary interruptions. And then we have load energy based indices that includes ENS, energy not supplied, AENS, average energy not supplied, and ACCI. And these are important for planning of power distribution network. So load energy based indices are important for planning of power distribution network. So what are the uses of reliability indices? Most utilities uses these one or more of the reliability indices to understand how the distribution system is performing. For example, some of the reliability indices which are formulated for sustained interruptions may not reveal momentary interruptions. And if you see the cost associated with system reliability are of investment cost, customer interruption cost, or customer damage cost. So customer interruption cost, customer damage cost are customer side cost, and investment cost is used to achieve a desired level of reliability. While customer interruption cost includes the cost of production loss for process industries. Customer damage cost, that is, if applicable, in that case, utility has to pay penalty to customer for power interruption. So reliability and cost generally conflict with each other, and that we see in the optimization part also. Means these two are conflicting with each other in multi-objective optimization problems, and where we have used the Pareto front approach to solve this multi-objective optimization problem, because higher reliability and lesser cost always conflict with each other. So we have to choose the optimal one. Now let us see the reliability indices. So reliability indices, you have to memorize this one. SAIFI means it is the ratio of sigma Ni upon Nt, and SAIDI sigma Ri Ni upon Nt. CAFI is sigma Ni upon Cn, and CAIDI means sigma Ri Ni upon sigma Ni. So just you go through this reliability indices. So this is about big five. So let us see the big five problems, and big five problems you just go through yourself because it is all are expression based. So you need to know the SAIFI expression, SAIDI expression, then CAIFI, CAIDI, ENS, AENS, ACCI, ASI, CTIDI. So in the last problem only, one theoretical problem asked which of the following is the correct value of the sum of the reliability function and the unreliability function. So it is 1. So we know that the sum of reliability and sum of unreliability function is 1. So B is correct. Now let us come to the big 6 assignment. So in the big 6 assignments, we have seen the reliability in terms of system. And in big 5, we have seen the factors by which we can find the reliability. But now on system basis, how we can find how the system is reliable, whole the system is reliable. So here we have to define some important terms. And the first one is mean time to failure. So mean time to failure is the ratio of mean time to failure is the operation time or uptime, and it is the reciprocal of mean time to failure is mean failure rate, that denoted by lambda. and mean time to repair is denoted by R bar, and it is reciprocal of mean repair rate. Mean time between failure is the summation of mean time to failure and mean time to repair. So you can say that T bar equal to M bar plus R bar. And mean time between failure is also called as the mean cycle time. And the mean cycle time is defined as the average time that it takes for the component to complete one cycle of operation, that is failure, repair, and restart. So T bar equal to M bar plus R bar. Now we can define the availability and unavailability. So availability plus unavailability equal to 1. So availability means means a fraction of time component is up or healthy. Unavailability means the fraction of time component is down or component is out of service. So unavailability means the system is going for repair. So it is the ratio of mean time to repair upon mean time between failure. So R bar upon R bar plus M bar. While availability is the time for which the component is providing operation. So it is the ratio of M bar upon R bar plus M bar. Now reliability of a repairable component in series can be found with this expression, and for parallel we have to apply this expression. For parallel here, this careful because in numerator and denominator we have to take care of these units. Units should be same. If units are different, then there are higher chances of then you will get the wrong answer. Now for the parallel series combination, how we will find the reliability? If you have the reliability is given for each component. For series system, just multiply all the reliabilities. So it is R to the power n, while for parallel system it is 1 minus R, so on. And if we have m number of components connected in parallel, so it is 1 minus R to the power m. Now next things come is that hazard rate or failure rate. So the rate of failures in a given time interval is defined as the hazard rate or failure rate during the interval, and it is the probability that a failure per unit time happens in the interval, provided that failure has not happened before the time t1 that is at the beginning of the interval, therefore hazard rate. Our instantaneous failure rate is RT1 minus RT2 upon T2 minus T1 into RT1. And we have concept regarding this Barter curve. Here this shows this Barter curve, and this figure shows a typical hazard function that we know as Barter curve. And this curve shows the failure rate with the function of time. So in the first period, it is seen as an infinite mortality period. And the first period shows the infinite mortality period, which is the period of decreasing failure rate. So you can see this curve is decreasing, failure rate is decreasing. This initial period is also known as debugging period, break-in period, burn-in period, or early life period. During this period, failures occurs due to design or manufacturing errors. While for period 2 that we call as useful period, and the second period is known as useful life period or normally operating period. The failure rate of this period are constant, and failures are known as chance failures, random failures, or catastrophic failures since they occur randomly and unpredictably. And the last period is known as wear out period. This third period is known as the wear out period. The hazard rate increases as equipment deteriorates because of aging. So you can see this is failure rate is increasing in this period third, or as the components approach their rated lives, and if the time T2 could be predicted with certainty, then equipment could be replaced before this wear out phase begins. So let us see this big six problem. So here, first problem, they have this combination of reliability block diagram. You have to find the equivalent system reliability. So for this part, for this one part, you consider separately, and then we have this part also you considered separate. So for first part, it is 1 minus 1 minus r square, while for this part, you will get this much expression. So this is for one part, this, and if you do the square of this, then you will get this one. So whole for this one. And while this is for this one. So we'll get the 0.9550336. Now in the question 2 to 4, we have voltage is applied across a single phase load and load drawn by current is given. The applied voltage and the drawn current are printed by the following equation. You have to find the RMS voltage and current. So to find the RMS voltage and current, you have to take the DC square and the RMS of AC value. RMS square, a square of RMS values for AC quantity. 200 square plus 100 square plus 50 square. Similarly, for current, you will get 2 square plus 5 square plus 10 square. Now the displacement factor be found by, that is the uh, displacement factor, we also call it as fundamental power factor. So displacement factor, so both quantities are given. So here you can see this fundamental voltage is sin omega t, while fundamental current is sin omega t minus 30. So displacement power factor is 30 degree. Power factor angle is 30 degree. So cos phi 1 is 0.866 lab. Now find the total harmonic distortion of the voltage and current. Guddu, do you know what the meaning of THD?
But sir,
What is the meaning of THD?
TSD,
Yes,
TSD, total harmonic distortion, sir.
yes. Total harmonic distortion means what is the means how much proportion of harmonics in your AC quantity. Like other
Total,
means it is reciprocal of RMS of other quantities, means greater than fundamental B2 square plus B3 square,
here is
so on
B1,
upon.
B1 is not there, sir. Why, sir?
Yes,
B1 square is not there. Why? In the
because
root.
we are fine. The top one is the, you can say that these are harmonics component that are undesirable frequency component available in the quantity. So we are not taking the fundamental component. So it is with respect to fundamental component, that is desired one, right?
Okay.
All the terms like V2, V3, V4, all are harmonic terms. That's why in the numerator we will take the RMS of harmonic terms on V1. So THD for voltage and current you can find here. Now in the question 5, failure rate of a distribution feeder is this one and mean repair duration is this one. Determine the mean time to failure. So you use the expression. So we'll get this one. Determine this availability of the feeder. So availability is MT upon total mean time to mean time between failure. Availability you got 99.99%. Rate of failures in a given time interval is known as hazard rate. So A is the correct option. In bathtub characteristics, the region where failure rate is almost constant is called as useful lifetime of a particle system. So question 9 and 10. This is the combination of series or parallel system. So you can find that. Next comes the our load flow solution for the distribution system. So now we have we can see various power quality issues in power distribution networks. So custom power devices used for power quality improvement. They are of two types: reconfiguration type and compensation type. Reconfiguration type, the network configuration devices are usually called switchgear, and they include current limiting, current breaking, and current transferring devices. And the and the sorry, and the examples for reconfiguration type for power quality improvement: solid state current limiter, solid state breaker, solid state transfer switch. And for compensation type, we have these type of devices either compensate a load or improve the quality of supplied voltage. And these are of distribution STATCOM, distribution static compensator, dynamic voltage restorer, and unified power quality conditioner. So unified power conditioner is combination of both DSTATCOM and DVR. So in this question, they are asking which of the following is used in the distribution system. So solid state breaker is not a compensation type, so it is wrong. DVR, yes, it is used. The STATCOM is used in the transmission system. Next come is that which of flowing is of long duration voltage variation. So long duration voltage variation and short duration voltage variation. What is the difference? Short duration voltage variation sustains for a few cycles up to 1 minute, while long duration voltage variation sustains for a periods more than 1 minute. So long durations can be classified as over voltage, under voltage, and sustained interruption, while short duration can be classified as voltage sag, swell, and interruption. Now, next come the load flow analysis of radial distribution network. So in that we have seen the backward forward load sweep method. So load flow studies are performed to know the steady state operation of a power system. In power system, powers are known quantity rather than connects. Thus, the equations used in load flow studies are in terms of powers. These power flow equations are non-linear and solved by iterative techniques. Load flow studies are used for planning, operation, economic scheduling, and exchange of power with utilities. Transient contingency and stability studies are used for the load flow analysis. So, backward forward sweep load flow algorithm is used for radial distribution network due to the following special features. Newton Raphson and other transmission network algorithms are failed with distribution networks, and these are radial and weakly mesh networks. We know that transmission network are of mesh type, while this distribution network is of radial or weakly mesh networks. It is having higher Rx ratio, and this incorporates distributed generation also. Now, what are the steps for load flow analysis of radial distribution networks? So the steps are: first to draw the single line diagram for a typical distribution network, and then prepare data file where we have node data, line data, and we generally take select node as the node 1 while load node be represented as 0. So select node or substation node represented by type 1 while node nodes are represented by 0. So in select node we have voltage and angle is defined. So one at the angle of 0 degree and active and reactive power. It is found at the end based on the power whatever the remaining power need to be exchanged to the to the customers. And then we have line data, NS, NR, line resistance, line reactance. Now we convert all the quantities to current quantities on appropriate base quantities, and then we will start the load power flow algorithm. So, so what are the steps for load flow algorithm? First, you calculate the current of each load. Load current at bus I. We know that S equal to VI conjugate. So from this expression, you can write I equal to P minus JQ upon V conjugate. Now you calculate the line current starting from the end of feeder. That's why it is called as backward shift. So it starts from the backward. And then for finding the line current, we will find the voltage of each bus node starting from the first bus. Then that follows the forward path. That's why it is called as backward forward load sweep load flow algorithm. Here we have assumed while solving this problem unidirectional flow power. We can determine both voltage profile and power loss of networks. Firstly, line currents are updated in backward sweep, and then node voltage are updated in the forward sweep. So in backward sweep, we determine the branch or line current, that is application of KCL, and its computation starts with the end nodes or terminal nodes. It needs more computation, while in forward sweep, we determine the bus voltage and it is application of KVL, and the computation starts with the select node. What are the termination criteria for this backward forward loads sweep load flow algorithm? Termination criteria are either one of these follows. First is that we have to set the maximum number of iterations which need to be restricted or error in node voltage from previous iteration to current iteration or measure of convergence. So magnitude of all node voltage iteration, you have to just record all this data and you will find the error in node voltage from the previous iterations. If error is less than some tolerance or accuracy, then we need to terminate the program. So first case is that if this maximum number of iterations approached, then we have to terminate the program. Otherwise, if error is less than this tolerance, then we terminate the program. Now in this problem, it is asked that what is the termination criteria for forward backward sweep load flow them. So as I already told you, there are two criteria. Either one has to fall, either one has to just fulfill, then we stop the algorithm. The criteria are either it satisfy the maximum number of iteration or it maximum number node voltage error between iteration and previous iteration. And this is pseudocode for forward backward sweep load flow algorithm where we have specified ideal maximum accuracy, then specify the base values, base voltage and base VA, call data file, node data and bus data, and then we have current conversion, active reactive power demand, line assistance reactances, and current conversion process is like this one. And then we will apply this code that it will start from the one, and then we will apply the while loop. So if it lies between these two data, then if it is satisfied, then perform the next step and to do backward sweep and forward the sweep. After performing this, we will get the updated voltage and the iteration count increased, and then we will determine the error and we will again provide back to this while loop. So let us see the problems based on the big 7. So the first problem is that in the backward sweep of the backward forward sweep method, which quantity is calculated first? So we know that line currents are calculated first in the backward forward sweep method. The forward sweep in the backward forward sweep method involves updating the node voltages. After finding the line currents, we update the node voltage in forward way. Which of the following assumption is essential for backward forward sweep method to work efficiently? The networks must be radial. The backward sweep in this one is wrong, it is not needed. The backward sweep in the backward forward sweep method involves calculating power loss in system, voltage drop across branches, line current from the load nodes back to the source, node voltage from the source to load. Backward sweep, so we find the line currents. So here it is asking that iteration continues until, so iteration continues until the node voltage mismatches are below a threshold and below a tolerance value. In a backward forward sweep load analysis, the slack bus is typically the substation node or root node of the critical network. The backward sweep in backward forward sweep method starts at the end nodes. So for question 8 to 10, you just apply this expression where we have used this x is equal to vi conjugate, or you can refer my tutorial slides, solve this type of problem. You will easily get that. So we have covered the big 7 assignment also. Gudu, do you have any doubt till big 7?
uh, uh, at point threshold means, so what in the questions, one point, it is a threshold.
Threshold.
Threshold, yes sir. Threshold, what is threshold, sir?
In the slide or in the problems? Here, right. Node voltage mismatch
Yeah,
below threshold, right?
it's a threshold, sir. Node voltage mismatch are below
Yeah,
threshold.
you have to define some threshold value. This tolerance or accuracy the same. This error is less than some threshold, you can say our tolerance or accuracy, then you need to terminate the program. Either it is like very small quantity 0.001 or 0.01 like that. Means you are updating the voltage at nodes in each iteration, and after that you see that you got voltage in some iteration like you got some voltage 0.98, and in the next iteration you will get 0.988, and your tolerance is 0.01. So it is within the tolerance, so you have terminated the program because you got the final result, right?
Yes.
So now we have the reactive power conventional addition system with shunt capacitors, that is big 8. So this one is regarding how you improve the power factor by applying capacitor at the distribution side. So this is the power triangle. We have this active power, then reactive power is present on the y-axis, and that with the help of power factor angle, we represent this apparent power. Next, we have this addition of capacitor bank at the load bus. So we have initially Q amount of lagging reactive power demanded, and now after adding this capacitance, this QC amount of power is being provided by the provided by the capacitor bank. So the net reactive power demand from the substation side is Q1 minus QC. So therefore you can see this power factor improves and power factor angle reduces. So cos theta 2 becomes like this one. So this is the example for power factor correction. And this is the illustrative example for the reactive power, for the effect of reactive power on power factor, where you can see this as we have considered the active power same in all the cases. As the reactive power increases, this power factor deteriorates. In the next case, we have assumed the apparent power same, and you can see that when this reactive power increases, active power reduces and power factor also deteriorates. Now, what is the concept of leading and lagging lagging power factors? The concept of lagging and leading power factor is that it depends upon the direction of flow of reactive power, and it depends upon the characteristics of either it is of load or it is of generator. So when power factor is lagging for load, that means Q is positive, load consumes reactive power, or load, if simply reactive power is written, that means it is of lagging in nature. So load consumes lagging reactive power and load supply leading reactive power. And if power factor is leading, that means Q is negative, that means load supply reactive power, load supply lagging reactive power, or load consumes leading reactive power. So this type of load we call it as capacitive in nature. Then you can define, you can correlate with generator. So for load you can say motor. So sign convention is positive because characteristics of load is that it consumes something. So if it's consuming real reactive power, then convention is positive, and for generator it's positive when it supply real reactive power. Now reactive power compensation of distribution system with shunt capacitors. So first we will define the lambda. So lambda is defined the reactive current at the end of line segment to the reactive current at the beginning of line segment. And for uniformly distributed load, this I2 becomes 0, so lambda becomes 0. And if for lumped load, I2 will be I1 because reactive current at the end of segment or beginning of segment will be same because the load is concentrated. So lambda is equal to 1. Therefore, alpha equal to 1 upon 1 plus lambda square. Now we'll define the C. C the degree of capacitive compensation. So C is the ratio of kVA of capacitance installed upon total reactive load. Now you can find the per power loss reduction expression. So this is very important. One of the question asked on this uh, single capacitor bank placement, and what is the per unit power loss reduction by placing the capacitor bank at a specified place. So X is the per unit distance of the capacitor bank location from the beginning of the feeder segment. Now analytical method for capacitor bank placement. So optimal power loss reduction comes out this expression, and differentiating between two C n equal to 0, you will get the C value 2 upon 3 and x1 is equal to 2 upon 3 1 minus 1 lambda, and power loss reduction expression will become set upon 9 into alpha 1 minus lambda, and if lambda equal to 0, that is uniformly distributed load, this power loss reduction will be 8 9 per unit, and capacitor placed at x1 equal to 2/3 per unit, distance with C equal to 2/3 per unit side. So this is the well known 2/3 thumb rule of capacitor placement. So now let us see the big cat assignment. So as I told you, this first expression is very important. So here they are asking about that this capacitor bank rating is given and this placement is also given. You have to find the loss reduction. Find the power loss reduction. So you have to use that expression. Now for question 2 to 7, you have to find the These are very easy. First one you have to find the active power, and then you have to find the apparent power, and then you have to find the again active power. Sorry, then you have to find the power factor, and then you have to find the capacitor bank rating. After place capacitor bank rating for the power factor correction, and then voltage drop. Voltage drop is I into Z. And the next problem, you have to find the load demand supplied in MVA after capacitor placement. So these questions are not that much difficult. You just go through tutorials as problems, quickly you will able to solve these problems very easily. What are the outcomes of power factor compensation? So the options are reduction of power loss, power factor correction, reduction of capacity limit, increasing voltage drop between sending in and source. So C and D are incorrect option. A and B are correct. We have reduction power loss and power factor correction. Why C is not correct? Guddu, can you tell this answer? What are the outcomes of reactive power compensation?
The reduction of power losses and power factor correction. It is the correct answer, but reduce the ampacity limit of feeder and increase the voltage drop between sending and source. Reactive power.
No, I am asking that why C is not correct? Reduce the ampacity limit of feeder.
Ampacity limit of feeder is not belong to the reactive power compensation. So
Yeah,
it
it is
is
the characteristic. It is the characteristics of line. There is nothing less with reactive power compensation. Yes, very good. So both A and B are only correct. Now in assignment number 9, it is related to economic aspects of power distribution planning. So let us see the big 9. So here first we will see the embedded cost, marginal cost, and incremental cost. So in embedded cost, the portion of cost that exists in the current plant system or configuration or level of use. Depending upon the application, this can include all the portions of the initial fixed cost and all are parts of variable cost. Marginal cost, the slope of the cost function at the current operating point. This point is usually the point at which the current immediate cost is defined. So incremental cost, the cost per unit of a specific jump or increment. For example, incremental cost of serving an identical 17 MVA from a certain substation or incremental cost of losses when load on a periodic exam of 5.3 to 5.0 MVA. So marginal cost and incremental cost both express the rate of changes of cost with respect to base variable, but they differ substantially because of the discontinuities and non-linearities in the cost relationship. Therefore, it is important to distinguish clearly between these two. So you can see this marginal cost has a slope while incremental cost has a slope with to and fro. So marginal cost has a slope while incremental cost has slope with a starting point and the ending point both are provided. Now we have to know about discount rate and present worth factor. So present worth factor is defined as the rate of discounted and it is the ratio of it is reciprocal of 1 plus d where P is present worth factor, D the discount rate. Let FW is the future of value of money required T years after and PW is the present worth of money for expensive planning. Then it is related by this equation present worth equal future worth into this present worth factor upon power T. Now next we have one important expression that is levelized value. Levelized value is the analysis of applying time value of money analysis to initial and future cost to develop an equivalent constant annual cost. So it is like that you require this much amount of money at some instant of time later. So what amount of money you need to invest early so that you will get that amount. So you can see that you can correlate with nowadays we are having a SIP. So systematic investment plan. So you can correlate with that. In SIP, you have choice like you can daily invest monthly or yearly, but here they are telling about early. But like that, you have to choose early. Means you have to equivalent constant annual cost such that it will having that amount of money for a certain given discount rate. So this is all for big nine. Now let us see the big nine problem. So the first problem is very easy. It is related with present board, future board, and present board factor. So you can get this discount rate. And the next question is based on the levelized value. So you need to know this expression levelized value expression Q equal to levelized cost equal to P into D into 1 plus D upon N, 1 plus D plus N minus N. So N is the number of years and Q is the present bought money. So be careful. Q is the present bought money. Now the dynamic planning of power distribution system involves it is multi-step planning with consideration of load growth. Which is like not a meta-heuristic optimization approach, mixed interprogramming and dynamic programming are not meta-heuristic optimization. These are mathematical based approaches. The determination of solution using meta-heuristic optimization will work with meta-heuristic rules inspired by nature of process and iterative updating of randomly generated solution. So mixed integer that contains both discrete and continuous decision variables. So again, this question is based on the levelized value. Just be careful. You have to just keep noted down that Q is the present worth of money in levelized cost expression. Now next problem they have been asked about from the evolutionary algorithms. We know that evolutionary algorithm can provide a set of Pareto approximate solution using multi-point search in single run, and the convergence is not always granted. So it is incorrect. C option is correct. Convergence evolutionary algorithms can handle convex as well as non-convex problems and do not suffer from the curse of dimensionality. And the last problem, there are ninth problem, they are asking about the incremental cost. So incremental cost can be considered equal to marginal cost. Incremental cost is large, yes. Incremental cost represents the rate of cost which for to given base variable. It is incorrect. Incremental cost depends the cost per unit at the current operating point. Yes, it is incorrect. So both A and C are correct. If you see B and D are correct option. So these two are correct, but in this problem they are asking about incorrect. So A and C are incorrect option. Because here in this problem they are asking which of the following options are not. So incremental cost can be considered equal minus within cost large. No, it is incorrect. So that's why it is correct option for this problem. And this option is also incorrect. And dynamic programming is that solution approach unique using dynamic programming involves overlapping subproblems and optimal substructure, and this and can effectively tackle time dependent constants. So just quickly go through the all assignments solution. Now for big 10, you can also refer to the summary I have provided, but you can first important thing that you just quickly revise all the problems. So here it is asking about the optimization planning needs for expansion. So it is determination of both feeder routes and branch conductor sizes. So we have covered all these type of problems in the tutorial assignments. You just quickly go through all these, and I hope you will able to understand and able to answer in the exam also. Okay, all right. So you can revise the rest part. Mr. The rest part are already have been covered recently, so that is not more important to revise. So we have revised till the big 9. So it's very good. Within 2 hours, we have revised 9 tutorials. That's very nice. And that are older ones. So from the big 10, it is all like optimization part and this distributed generation, a smart grid and automation and all these things. Wind energy conversion system. So we have covered them recently. So that there is no need to, I think, revise all these things more. Gudu, are you able
Yes,
to
sir.
do you have any doubt?
No, sir. So,
You are from an IT partner, right?
yes, sir. Yes, sir. Nati Patna PhD first year, sir.
Okay,
Second semester,
nice,
sir. So
nice.
two subjects in the credit of for the exam. So 10 credit completed, but overall 16 credit completed, sir. So six credits only remaining. Sir. 3 credit this subject and another control engineering the three credit. Total 6 credits,
So
sir.
this course
Remaining.
is only of 3 credits, right?
Yes, sir. Yes, sir. 3 credit this subject and another subject is taken three credit. Overall six credit needed.
Okay, just I suggest you that you revise all the assignment problems and all the previous year assignment problems. You will get
Previous
the.
year, it is not available, sir. The previous year. So
No, I am providing in my session. That is only previous year.
uh, well, every lectures in the included previous year questions.
Yeah, I am giving you this previous year assignment solution also with respect to this Miss 2024 assignment problems
24,
like 20,
24
23, 20.
assignment.
Yeah,
Overall,
so you can get from there.
okay, sir.
If
23
you
and 24, 23 and 24 questions consist in the tutorial, sir, for solving.
I have covered 22, 23, and 24 3 years assignment problems. I have solved all 3 years assignment problems in the live session. So you can
Okay, sir.
get you can
Every
revise from slide.
every note, all notes are briefly uh, study and every questions are practices is important.
Yes, means all the at least assignment should be it needs to practice. Means without assignment it's very difficult in the exam.
Yes, sir. Yes, sir. So number of questions in the assignment 2025 are similar in the 2023 questions. So both are
Yeah, correct,
related.
correct.
So
2025 problems are most similar to 2023, and
yes, it is
exam they will.
solved by you 2023 in numerical type in the tutorial, sir.
Hmm, yes, correct. So you just means do your best and all the best for your exam. And if you have
If I am
yes,
study in the tutorials lecture and PDF is the PDF are attached in the lecture notes is the thoroughly I study in the underline basis important points just like a numerical type question for solving uh,
yeah,
formula
yeah, it is enough. It is enough.
formula are noted and techniques are important for practice
Yeah,
are more.
yeah, that yeah. You just have a short notes before the exam also. I hope you will. That is not that much difficult exam. You have to just give exam for one course, and options are also given. So it's very not that much difficult.
Oh,
Okay, all the best for exam, and you can ask me in between also. Your exam in 27, right?
yes, sir, yes, 27 in the April.
I don't know when is the
So,
exam.
exam on the May, in May. Exam
Okay,
will
let
be
me see.
conducted on May, sir. 4 or 6 May.
Okay, let me see. I think they have initially announcement they have provided.
Listed in the exam listed, there is a mention in the schedule on
Yeah, my
May,
theorem.
May, sir. Yes, sir,
Yes, my
May.
theorem. Yeah, correct. Very good. So
See,
I think
yes,
hopefully you got the hall ticket in this week. I think so.
this week release, sir, hall ticket.
I think so because for 27th April they have just told about the exam date, exam venue, but they have not released the whole ticket. I think for 27 April they will provide this week, and for the within uh, uh, in the next week I'm sure that they will provide the whole ticket, or
Okay,
at least this venue for this exam.
27 on 27 April, there are two subjects I am applying, so hall ticket are released.
Yeah.
27.
Okay. Good. If you have any, you can contact me also. I hope you have my number also, right?
Any doubt in the matlab previous year questions? Any doubt I am asking you for uh, any
Yeah.
time.
Yeah. You can ask me on WhatsApp. I've given you my contact number. You can ask any things regarding the course.
Okay, sir.
Okay.
Thank you.
Okay. Bye. Good night.
Good night, sir.